Hello and welcome to our Reigate Maths video focusing on the mechanics section of the second year of the A-level maths. This is Simon, and in this video we're going to be looking at another application of forces, which is looking at inclined planes. So much like the previous video where we looked at ladder type questions, these are a multitude of different topics put together. So what we're talking about is particles sliding maybe up or down a plane. What this makes this different potentially to things you may have done before is we tend to include things to do with friction. So we have a particle held at rest on a rough plane, inclined at an angle alpha where tan alpha is 3/4. The coefficient of friction between the particle and the plane is 0.5. The particle is released and slides down the plane, and we want to find the acceleration of the particle. So clearly we have acceleration, we're going to have some forces. This is an F equals ma question. But first things first, let's label our diagram. So we don't know the mass of the particle, so to make our notation nice, let's call it m, which means the weight is going to be mg, and we know from our triangles this angle is alpha. What other forces are happening? Well, there's a reaction force because the block slides down the plane, and we know there's friction, which acts opposite to the direction of movement. How do we know it's moving down? Well, it slides down the plane. There's no force pushing it up. So we also know it accelerates in this direction. For this question, this is, to be honest, all that we need. So let's start putting numbers and things into, or writing down some formulae. So we know that F equals ma. So forces down minus forces up is going to be mass times acceleration, and acceleration is what we're trying to find. So we'll get there. Let's think about this direction first, because it makes life easier. Well, we know that R is going to be equal to this force here, this force here, and we know that's going to be mg cos alpha. Now, how do we work out alpha? Well, we could obviously actually work out alpha, but let's try and be more clever about it. If we were to draw a right-angled triangle different to this one, similar but different, with alpha at our base, well, from SOHCAHTOA, we know that tan is opposite over adjacent. So we know that this triangle is going to be some multiple of that. We don't know if exactly going to be that, but it's irrelevant. Looking at our triangle now, we can use Pythagoras to work out this length. 4 squared plus 3 squared is 25, square rooted is 5. So we know cos alpha is going to be adjacent over hypotenuse is going to be 4/5. So we can write down R as 4/5 mg. Now obviously I could work out that a little bit further. We know what G is. G is 9.8, but I'm not going to, and you'll see why later on. So that's one step. So if you're not sure what to do now, we've resolved this way, perpendicular to the plane. So let's resolve forces this way, parallel to the plane. Well, we know that forces down, because it's moving down, minus forces up is going to be mass times acceleration. So our forces down are going to be mg times sine of alpha. So that's going to be this length, or this force here, this component. So we've got mg sine alpha minus friction There are no other forces in play. And that's going to be equal to mass times acceleration. Don't forget, acceleration is the thing we're trying to find. Sine alpha, we can use our triangle again. Opposite over hypotenuse, 3 over 5. So we know this is going to be mg, or 3 over 5 mg. Friction, we know is mu r. So mu is 0.5 times r, which is 4 over 5 mg, is ma. So I'm just going to add a note here so we don't forget. Friction is mu r. So now we can tidy this up a little bit. We can see 3 over 5 mg minus 2 over 5 mg. We get a fifth mg. Is ma. And now can you see why I left everything in there? I didn't work out various numbers. I could have done, but it just meant we had to write less down. The m's cancel, so we know a is 1 over 5 times 9.8, which we just work out on our calculators to get 1.96 meters per second squared. So this is a much more straightforward application of forces than the ladder question in the previous video. But still, it's got some steps, and because of that, it can be a decent chunk of marks. Typically, 1 mark here, 1 mark here for using F equals mu r, 1 mark for attempting to resolve parallel to the plane, 1 mark for actually doing it correctly, and then 1 mark for actually working out A. So this question could very easily be 5 marks. We're going to look at a part B now, and it's this here. Find the distance the particle slides in the first 2 seconds. So given we're finding distances, clearly this is a SUVAT question. So we know from part A that acceleration is 1.96 meters per second squared. So that's from part A. So it's a SUVAT question. So what do we write down first? We write down SUVAT. Whether you write it across the page or down the page is entirely up to you. I write it down the page. So the distance, that's the thing we're trying to find. We know acceleration, and we're told time. What else are we told? Well, in the question, we're told the particle is held at rest. So we know the initial acceleration is u. We now just need to pick a SUVAT equation that uses all of these bits and doesn't have v in. It's a very common one. It's one you'll find you use a lot when we get onto later videos in mechanics. And it's ut plus a half at squared. So ut is 0 plus a half times 1.96 times 2 squared, which if we type in our calculator gives us 3.92 meters. Now in terms of degree of accuracy, technically we should probably only be giving to 1 decimal place, because that's what we used for G was accurate to. But if you put 3 significant figures, you'll also be fine. So these incline plane questions, it's just application of forces and friction. No moments involved because nothing's turning. It's just stuff sliding. So this is where forces go into SUVAT. Typically with a friction in there, maybe with other forces. You might have something pushing the box up the plane, something like that. But it's just variations on a theme. Thanks for watching.